This is Euclid Book 10, proposition number 53. And when I finish this proof, do not switch off this video. The reason for that is this video will also have a lemma. Not a lemon, a lemma. Okay? So when I finish this proof, we're going to cover this lemma right over here. So please do not switch off this video once this proof is done. Okay. Now then, we're now going to find the sixth binomial straight line. Okay? And I'm going to make sure you guys are seeing everything because I don't want you to miss anything. Okay, we're seeing everything at this point. Okay, good. Alright. Let two numbers AC, CB be set out such that AB has not to either of them the ratio which a square number has to a square number. Okay? So we have AC and we have CB. So that if you were to put AC to AB as a ratio, okay, it would not have what is a square number is to a square number. Same thing here. As CB would be to AB, so as a square number wouldn't be to a square number. And let there also be another number D. That is this one right over here. This is not a square. Okay? And as D is not to AB, as D is not to AB, and as D is not to AC, a square number is to a square number. That's fine there. Okay, now we're going to draw a rational straight line, and that's going to be E right there. Now let it be contrived that as D is to AB, we're going to set up a ratio now. As D is to AB, this whole length right here. So as the square on E is to the square on FG. This is by Euclid Book 10, proposition number 6, porism. Therefore, the square on E is commensurable with the square on FG. This is by Euclid Book 10, proposition number 6. E is a rational straight line. Therefore, FG is also a rational straight line. Now, since D has not to AB, so as this is to this, and it is not where a square number has to a square number, neither has the square on E to the square on FG the ratio which a square number has to a square number. Therefore, the length of E is incommensurable with the length of FG. And this is by Euclid Book 10, proposition number 9. Again, let it be contrived that as AB here is to AC here, so is the square on FG to the square on GH. And this is by Euclid Book 10, proposition number 6, porism. Therefore, the square on FG, this one right here, is commensurable with the square on GH. And that's by Euclid Book 10, proposition number 6. Therefore, the square on GH is rational. Therefore, the length of GH is rational. And since AB has not to AC, as this does not have to this, a ratio which a square number has to a square number, neither has the square on FG to the square on GH, the ratio which a square number has to a square number. Therefore, the length of FG is incommensurable with the length of GH, and this is by Euclid Book 10, proposition number 9. Therefore, FG and GH are rational straight lines. They're only commensurable if they're in square. Therefore, the whole length of FH is a binomial. And this is by Euclid Book 10, proposition number 36. It is next to be proved that it is also a sixth binomial straight line. For since, as D is to AB, as this is to this whole line right here, so is the square on E to the square on FG. And also as AB is to AC, so is the square on FG to the square on GH. Therefore, xi quali, as D is to AC, so is the square on E to the square on GH. This is by Euclid Book 5, proposition number 22. But D has not to AC. This does not have to this. The ratio which a square number has to a square number, neither has the square on E to the square on GH, the ratio which a square number has to a square number. Therefore, E is incommensurable length with GH. Okay. So these are commensurable, but this and this are not. This length is not commensurable with this length right here. And that's by Euclid Book 10, proposition number 9. But it was also proved incommensurable with FG. Okay, so this was proved incommensurable with this. Therefore, each of the straight lines, FG and GH, are incommensurable with E. This is incommensurable with E. This is incommensurable with E. And since, as AB is to AC, as this is to this, so is FG to GH. Therefore, the square on FG is greater than the square on GH. This is bigger than this. How much bigger is this is to this? Well, we're going to draw this line K right here. We're going to make a square out of it, which is this is right here. Okay. So now we're going to add this area and this area together, and it's going to be equal to the area of this. Therefore, convertendo, as AB is to AC, let's try that again. Convertendo, as this whole length right here is to this whole length right here, so is FG to K. This is by Euclid Book 5, proposition number 19, porism. But AB has not to BC. This does not have to this a ratio which a square number has to a square number, so that neither has the square on FG to the square on K, the ratio which a square number has to a square number. Therefore, FG, this length right here, is incommensurable with length with K. And this is by Euclid Book 10, proposition number 9. Therefore, the square on FG, this is greater than this. Okay. This is greater than this by a square, which is this square right here, on a straight line, which is this one right here, that is incommensurable with this straight line right here. And FG and GH are rational. Both of these lines are rational. And they are only commensurable in square. Okay, so this is commensurable, but these lengths are not. And neither of them is commensurable in length with the rational straight line, which was E. So this is not commensurable with E. This is not commensurable with E. Therefore, FH is the sixth binomial straight line. Now that concludes Euclid Book 10, proposition number 53. But we do have a lemma. And in just a moment, I'm going to present it. But I got to get something. I'm parched. And I do apologize for the brief pause. Here's this lemma. Let there be two squares, A, B, and B, C. Okay. Where's the first square? That's this one. Where's the second square? That's this one right here. And let them be placed so that DB is in a straight line with BE. Okay? So this is in a straight line with this. Therefore, FB, now where's FB? This is FB right here. Is also in a straight line with BG. So this is in a straight line with this. Let the parallelogram AC be completed. So this is one giant parallelogram. I say that AC is a square. Okay, we're going to say this whole thing, this AHCK, okay, AHCK, we're going to say that's a square. That DG is a mean proportional, okay, where's DG? That's DBGK, that's this one right here. Between, okay, this is going to be a mean proportional between AB and BC. And further, that DC, well, what's DC? Well, that's DECK. That's this whole area right across here. That's this plus this here. It's a mean proportional between AC and CB. Okay, what's AC? Well, AC is this AHCK. And what's CB? Well, that's CGBE. Okay. 4. Since DB is equal to BF, okay, DB is equal to BF. These two lines are equal in size. And BE is equal to BG. Okay, so BE here is equal to BG right here. Therefore, the whole DE, this whole line right here, is equal to the whole line FG. But DE is equal to each of the straight lines AH and KC. Okay, so DE is equal in length to AH. Where's AH? It's right here. This length is equal to this length, and this length is equal to KC. And FG, okay, this is FG right here, is equal to the straight lines AK. So this is the same length as this one right here, and FG is also the same length as CH. And this is by Euclid Book 1, proposition number 34. Therefore, each of the straight lines AH and KC, okay, well, AH and KC they are equal to the straight lines AK and HC. So AH is equal in length with AK. And KC is equal in length with HC. Therefore, the parallelogram AC is an equilateral and is also rectangular. So therefore, AC is a square. And since as FB is to BG, okay, so as FB is to BG, so is DB to BE. DB, BE. While as FB is to BG, while as this is to that, so is AB to DG. Okay, so now we're going to say that this square is to DG. Where's DG? This square is to this rectangle. Okay. So what we're really saying here on this one is, as this length is to this length, so is this square is to that rectangle. And as DB is to BE, as this length is to this length, so is the square DG, or the rectangle DG, is to BC. So, what we're saying here is this length is to this length, so is this rectangle is to that square. And that's by Euclid Book 6, proposition number 1. Therefore, also, as AB is to DG, as this is to this, now we're talking about areas now, as this area is to this area, so is DG to BC. As this area is to this one, so as this area is to that one. That's by Euclid Book 5, proposition number 2. Therefore, DG is a mean proportional. This is the mean proportional between AB and BC. I say next that DC is also a mean proportional between AC and CB. So now we're going to try to say that this whole area here, this one together, this whole area right here, is also mean proportional between the whole thing of AC right here and this little area right here. For since as AD is to DK, so is KG to GC. Well, where is KG? That's this one right here to this one. So as this length is to this length, so as this length is to this length. Therefore, they are equal respectively. And componendo, as AK is to KD, well, as AK is to KD, okay, so as KC is to CG. KC to GC. And this is by Euclid Book 5, proposition number 18. Wow, as AK is to KD, as this is to this, so as AC to CD. Okay? As this is to this, so as this whole area is to that little area. And as KC is to CG, as this is to this, so is DC to CB. So is that whole area to this area. This is by Euclid Book 6, proposition number 1. Therefore also, as AC is to DC, as this whole area here is to this whole area right here, this plus this together, so is DC to BC. So as this whole area right here is to this one right here. This is by Euclid Book 5, proposition number 2. Therefore, DC is the mean proportional, this whole area right here is the mean proportional between the whole area AC, which is all four of these, the two squares and the two rectangles together, and this little area right here, being what it's proposed to prove. Alright, you have learned a bundle here. I will tell you more in a future video, so stay tuned.